In this video, you will learn another important fact about triangles, and that's the triangle inequality conjecture. So for this particular video, I want you to think of this scenario. You have a drawbridge, and it's spanning a river. How long does each side of the drawbridge need to be so that the bridge spans the river when both sides come down? Now, if you look at it one way, if the two pieces of the bridge add up to be less than the span of the river, then when the bridge goes completely down, there'll be a little gap in between, and that wouldn't be good if you were trying to drive across that bridge. If the two parts of the bridge were exactly the same length as the span of the river, then it would look like how it is in the picture, but when the bridge came down, the bridge would meet at exactly one point. So if you think of the distance in between the two bridges as a line segment, and then the actual two pieces of the bridge as two line segments, when those two line segments came down, they would touch at a point, forming one line segment that would overlap the entire line segment that represented the span of the bridge. Now, if the two pieces of the bridge were longer, if they added up to be longer than the span of the river, then as the bridge came down, the bridge wouldn't be able to fully come down. Instead, it would sort of make a triangle with the two sides of the bridges being the shorter sides and the span of the river being the longest side. So, to answer this question, the sides of the drawbridge have to add up to be equal to the span of the river, and it would form a straight line. But if they added up to be more than the span of the river, they would make a triangle. So let's investigate that using Geometers Sketchpad. So, if we have three segments here, AB, AH, and GB, and AH stayed 5 centimeters, and GB stayed 5 centimeters, this is really annoying. When you tried to make a triangle, if they stayed 5 centimeters, you wouldn't be able to, because once you started lifting these sides up, even if they were exactly 5 centimeters, there would be a little gap in between. And it's hard to get close with this, but just bear with me. So say they're both exactly 5 centimeters, notice the gap right here. So in order to make a triangle, the two shorter legs have to be longer than the third leg. So if we look at these two shorter legs, side BG is 5.5 centimeters, side AH is 5.5 centimeters, so their sum adds up to be more than the longest side, 10. And if they don't, let's say one side is, let's say one side is 7. But if the other side isn't 3 or greater, let's say it's like 2.5, then no matter how I adjusted this side, it would never meet the other end. Alright, let's look at another example of a triangle already made. And I'm going to adjust these sides so that side P is always the longest. Alright, so if you notice, we have the measures on the left here, and also has the sum of the two smallest legs. So notice how it's always bigger than side P. Even if I make M and N as small as possible, if I make angle A and angle C both 3 degrees, alright, M plus N will still add up to be more than P, the longest side. So, just another example of that the sum of the lengths of any two sides of a triangle has to be greater than the length of the third side. And you can always check that by just checking the two shortest sides. If the two shortest sides add up to be greater than the third side, then you know that you can make a triangle because of the triangle inequality conjecture. So let's try to apply that a little bit. So again, one more time. The sum of the lengths of any two sides of a triangle is greater than the length of the third side. And again, you can always test that by just checking the two shortest sides. Because if the two shortest sides add up to be longer than the third side, then any two sides of the triangle will add up to be longer than the third side. So, if we look at the example on the left, can you make a triangle that has side measures of 3, 4, and 5? The answer would be yes. And you can check it because the two shortest sides, 3 and 4, add up to be larger than the third side. But if we look at this example on the right, that would be no. Because if you checked if you picked two of these sides and checked that they add up to be bigger than the third side, when you checked 8 and 6, the two shortest sides, that equaled 14, which would be less than 15, the third side. So therefore, you cannot make a triangle that has side lengths 8, 6, and 15. If you tried to, it would sort of look like a drawbridge like this, where one side was 15, one side was 6, and another side was 8. When these sides sort of came down, they would never touch, because 6 and 8 do not add up to be more than 15. Let's look at one more conjecture, I believe. And that, well, actually no, let's look at one other type of problem, and that's determine the range of the third side of a triangle if two sides have length 4 and 8. So what's the shortest that the third side could be? So for this example, since we're looking at what's the shortest the third side can be, assume that 8 is the largest side of a triangle. So we know that 4 plus the angle that we don't know, if x is the shortest side, then we know that 4 plus x has to add up to be greater than 8. So if we solve this and subtract 4 on both sides, we know that x has to be greater than 8. If it's, or 4, sorry, because 8 minus 4 is 4. And that makes sense, because if x was equal to 4, then 4 plus 4 would equal 8, and that wouldn't work because the two shorter sides have to add up to be larger than the third side. But if it was anything bigger than 4, it would still work, except if it was too big. So now assume that x is the largest side. So if x is the largest side, x has to be less than the sum of the two other sides, the two shorter sides. In this case, we'll assume it's 4 and 8. So x also has to be less than 12. So what are the possible ranges and lengths of the third side? Well, we have to make sure it's less than 12, because if it's greater than 12, then when you add 4 and 8 together, they won't be greater than the third side. And it also has to be greater than 4, because if it's equal to 4 or less than 4, then when you add it to the other side length that's 4, it won't add up to be more than 8. So that is our answer. Now, let's look at one more conjecture, and that's the side angle inequality conjecture. So let's look at this through Geometers Sketchpad, and we're going to pull up this same Geometers Sketchpad, except I don't want you to focus on the side lengths now only. I want you to focus on the angle lengths and the side lengths. So if I adjust it to be sort of like an equilateral triangle, all right, I'll make it as close as I can get. If we look at angle C, which is also written as angle BCA, that's 52 degrees. Opposite angle C, which is 52 degrees, is N. And side N has a side length of 2.5. So the shortest angle is opposite the shortest side. And if we look at the largest angle, BAC, which is also the same thing as saying angle A has an angle measure of 65 degrees. And that's opposite M, which has a side length of 2.8, which is the biggest side. So in this case, in a triangle, the longest side is always opposite the angle with the greatest measure, and the shortest side is always opposite the angle with the least measure. All right, and it makes sense, because if we pull out this side C to make side P very, very, very large, notice how angle B gets smaller. So now angle B, or angle ABC, is 115 degrees, and the side opposite of it, P, is 10.4. And if we make side N very, very small, we notice that at the same time, we're making angle C, or angle BCA, very small. So if we make angle C 1 degree, notice how minute side N is, 0.2. So now the smallest angle is opposite the smallest side. So for this side angle inequality conjecture, think of like a mouth of an alligator. Right? If the mouth of an alligator is barely open, so you have a very small angle, the distance between the teeth is going to be very small, or the side. If the angle or the mouth of the alligator is open very wide, then the distance between the teeth will be very far, meaning the side is very long. So again, the longest side is always opposite the biggest angle, and the smallest angle is always opposite the smallest side. So let's use that conjecture to help us order these variables. So the question on the right, or I'm sorry, the question on the left is a lot easier. It says order A, B, and C, because those are the variables, from largest to smallest. So we look at the largest side first. That's going to be 5. So we know that angle B is the largest angle. So we'll put that first. And then angle C is opposite 4, which is bigger than side 3. So C has to be bigger than A. So the answer to this question on the left would be B is the largest angle, C is the smallest, C is the medium, and A is the smallest angle. Alright, the problem on the right is a little trickier. Whenever you have two triangles that are overlapping or sharing a side, then what you want to do is first order the measures of one triangle, then order the measures of another triangle, whether they're sides or angles, and then compare those measures. So first let's look at the right triangle with sides R, T, and S. Well, we know that angle R is we know that side T is the biggest side because it's opposite 90 degrees. And then angle R and S, since they're both opposite 45 degrees, they have to be equal. So we know that this is an isosceles triangle on the left. Alright, so that's the first thing that we know. The second thing that we know is in the obtuse triangle, angle U has to be the biggest, side U has to be the biggest side because it's opposite the biggest angle. And then V has to be the second biggest side because it's opposite the second biggest angle. And then T is opposite the smallest angle, so it has to be the smallest side. So now, for our final answer, if we look at these two orders that we have, T and then R and S are equal, and then U, V, T, we can conclude that out of all these sides, R, S, T, U, and V, U has to be the biggest because U is bigger than V and T in the obtuse triangle, and since T is the largest side in the right triangle, then U and V have to be larger than T, R, and S. So when we label this, it's going to be U, V, T, and then R and S in any order. Alright, but one thing you don't want to do is say that angle U is the biggest side, and then angle T is the second biggest side, because that's opposite the second biggest angle. Alright, the side angle inequality conjecture only works when you're looking at one triangle, because you can have something like this. Alright, so you can have something like this. We have a very small obtuse triangle, so this angle measure right here, I'm going to say is 150 degrees. But let's say it's sharing a side with this triangle, which clearly, by looking at it, has these two sides right here are going to be bigger than this side right here. But this side right here that I just highlighted is opposite 150 degrees, but this angle right here could easily be like 62 degrees. This angle could be 62 degrees, and this angle could be 54 degrees. And although this side right here is opposite a smaller angle than this side over here, they're in two separate triangles. So one triangle could be scaled up a lot larger than the other triangle. The last thing that I want to talk about, no, I don't want to do that. The last thing that I want to talk about is that since we know that the largest side is opposite the largest angle and the smallest side is opposite the smallest angle, if we have an equilateral triangle, we know that, well, since all the sides are equal, all the angles have to be equal. So every equilateral triangle is equiangular. And if all the angles are equal, that also means all the sides are equal. So every equiangular triangle is equilateral. That is it. Thank you for watching, and I hope that was informative.